Hello everyone, welcome again to my YouTube channel, The Learning Hub. So till now we have learned about a lot about supervised learning. We have discussed linear regression, logistic regression. We have done the implementation in Python. We have discussed about various performance matrices in that, and in today's video we are going to discuss about support vector machine. So when we talk of support vector machine, firstly we need to understand that this is a technique that is used for classification. It works on what? It works on label data because it is a supervised learning technique. So when we talk of support vector machine, also known as SVM, it is one of the popular supervised learning algorithm which is used for classification as well as for regression problems. Its primary use is for classification problems in machine learning. It came into existence in 1960s and now get refined in 1990s and still in use. SVM have their unique way of implementation as compared to other machine learning algorithms because it works on decision boundaries. It has a decision boundary which separates two classes, separates the data into different classes. So it creates a best line of decision boundary that can segregate n-dimensional space into classes so that we can easily put the data point in a correct category in the future. Like it works like this, a line which is differentiating data points of class 1 and here data points of class 2, and we get a best fit line. And basically this line which is drawn is known as hyperline or hyperplane in support vectors. So when we talk of this technique, we have support vectors. These are the terminologies that are being used. Support vectors are there. We work on decision boundaries. And we have hyperplane. So these are the main key points when we talk of support vector machine. So here the decision boundary that is being drawn is called a hyperplane. Here SVM chooses the extreme points of the vector that helps in creating the hyperplane. These extreme cases are called support vectors basically, and this algorithm, that's why is known as support vector machine algorithm. So let's see how it is work. It works by basically differentiating the classes with the help of a hyperplane in the multidimensional space. The hyperplane will be generated in the iterative manner by SVM that we can minimize the error. So if we look at this diagram, along the x-axis and y-axis we have certain points, and here we are having two classes, class A and class B, and between these two classes we have a margin line. And this line is basically separating the two classes into two different points. Now when we talk of hyperplane, we must say that suppose there are two classes like this, and we are classifying the classes in this way. We could have used either this one, or there may be line which may separate in this direction and so on. But the hyperplane basically goes this way because there is a reason behind that. We will also discuss the reason in that case why it is happening in this case. So when we have a look at this, along the x1 and x2 are the points, and where we are having a few points, maximum margin hyperplane is the target that we have to achieve. As we can see, here are these green circles which are class 1, and these blue squares that belongs to class 2, and this is a line. This is separating these two classes, two types of data points into different classes. And here we are having different points like decision boundaries. This is basically called a decision boundary, and we are having two lines. So the goal of SVM algorithm is to create the best line, or that is also known as decision boundary, that will segregate n-dimensional space into classes. We can easily put the new data according to a category in the case. Now let's have a look at this, how it is working. Suppose I am having points like this. Here I am having, suppose, circles. Fine. And suppose here I am having rectangles. Fine. These two are different classes. Now here we can say there is a line. This is also separating these two, and line can be in this direction also, which can separate these two different classes. But why we are talking of a hyperplane which is not a straight line in this direction, horizontal or vertical? There is a very good reason behind that. Now let's understand what is that. So let's consider the same example, having triangles over here, having circles over here, and this is the hyperplane, the decision boundary. And we also draw two parallel lines here. Here we are having a line. We also draw a line over here like this. So now what are these two lines playing the significance? Basically these are positive and negative hyperplane. Along this side we have negative, along this side we have positive. Now if you have a look at this dotted line, what is this? This line is drawn very close to one of the data point, exactly touching, almost touching this data point. So inside this class, like if we say have a look in this class, then the line will go something like this, which will be touching the closest point with minimum distance from this class. And similarly, if we look at this class, suppose we are having a point over here, then there will be one line that will be drawn parallel to this, so which is very much close to this minimum distance from a data point in this class, and one line in this class which is having minimum distance to a data item in this class. Fine. So we have drawn these two parallel lines, and between these two parallel lines we draw one of the decision boundary which is exactly passing through this. And what is our target over here? To get this distance maximized. So we have to get maximum margin in this case. This maximum margin will represent the best categorization. Like if I say I have to divide a few data items into two groups, what should be my target? The distance between those two, or the separation between those two groups, be as much maximum as possible, because the maximum will decide the best categorization. So that is what we are doing over here. So our target is to get this much distance as high as possible. Now suppose in this case we are having something like this, points over here, points over here, and we try to draw a line like this, then we are not getting that much hyperplane. Similarly, not getting in this direction. So we can have here also. So I can draw a line like this, but in this case a dashed line will be played over here with minimum distance like this. So this is a distance. Also in this direction one hyperplane line is this, and these two dots, and this is distance. Let us call this distance d1, that is this marginal distance. Let us call this distance d2. As we can see over here, we have drawn line in this direction and here in this direction, but here we can say d2 is greater than d1. So it means d2 is high distance as compared to d1. Now when we have a look at this, this difference gives more clear separation between these two classes. So that is what a hyperplane is. This marginal distance should be as high as possible, and that is what is our target, to get the maximum margin. And with this margin, along one side we have this positive hyperplane, and along this we have negative hyperplane. So as we can see over here, this is maximum margin, this is positive margin, and this side is negative margin. Now let us understand what support vectors here mean. So support vectors are nothing else the data points, like here and here. The data points that has played a role in drawing this line, this separation line. Fine. So here see, this dashed line is very much close to this data point. Fine. And here is this line, which is this line, this is close to this data point. So we are having these two parallel lines, positive one line over here, one line over here, and the closest point to these lines, which is giving the margin, is known as support vectors. So support vectors are nothing else. Support vectors are basically the data points, one from each class, that is closest to these lines, which is giving the separation between two. So that was the linear hyperplane, which we can draw a linear line. The separation can be done on 2 dimensions. But what happens if we get something like this? Now suppose this type of data points are there. So what will happen? We can't draw any line. This line will not give any separation. This will not give any separation. This will not give any separation. So this is a case when we can't go with this linear SVM. So in this case, we have to proceed to look for the alternative that is not simply linear but is giving certain other clear separation. So which should be like this. Now let's have a look at this diagram again. So we were having something like this. So what can we do? We can draw some line like this, which will give the separation between these triangles and these circles. This is not a linear line. So here this is a curvical shape or anything X that needs one more dimension, let us say on the Z dimension in the space. So that is being represented over here. So you can say this area will give space, and this blue is nothing else. This is simply hyperplane in this case, which is giving separation between these yellow and red dots. So support vectors, we have discussed that the data points that are closest to the hyperplane, separating line will be defined with the help of these data points. And hyperplane is nothing else, it is a decision plane or space which is divided between a set of objects having different classes. So there can be multiple lines, decision boundaries to segregate the classes in n-dimensional line, and we found out a best decision boundary. In this case, we are drawing on 2-dimensional as well as multiple dimensions also. We always create a hyperplane that has maximum margin that we have discussed. It may be defined as the gap between the two lines. It can be calculated as the perpendicular distance from the line to the support vectors. The goal of a support vector machine is to divide the data sets into classes. That is what we have to do. Basically, we have to do classification, and we have to find the maximum marginal hyperplane. It can be done by first SVM will generate a hyperplane iteratively that segregates the classes in best way. Then it will choose the hyperplane that will separate that. Now let's take an example in which we suppose that we have to see in this case. Let's have a look at this example. Here we are talking about a classifier. So we see a strange cat that also has some features of dogs. So if we want a model that can accurately identify whether it is a cat or is a dog, so such a model can be created by using SVM algorithm. We will train our model with lots of images of cats and dogs so that it can learn about the different features of cats and dogs. And then we test it with some strange creature. So as support vector creates a decision boundary between these two points, that is a cat and a dog, and we are asking a question on this, then it will predict based on certain categories that it is a cat. So basically here we are training our model with lots of images, and then we will test it with certain creature. So as support vector creates a decision boundary between two data and extreme vectors, it will see that the extreme case of a cat or dog, on the basis of a support vector, it will classify it as a particular category. And the two types are linear SVM, as we have seen in the example, which is like this, in which we can divide the classes into two parts based on this hyperplane. But when we are having data items like this, and we can't get any clear separation and we have to go this way, that is known as non-linear SVM, which is used for non-linearly separable data, which means if a data set cannot be classified by using a straight line, then such data can be turned as non-linear classifier. So this is the example of linear SVM, in which we can draw one line over here and here one closest line passing through this, and one line will be in this direction. So this is the margin, maximum margin, and this is my decision boundary, and this area is my hyperplane. So this is basically clear a linear SVM, and this point and this point, this is support vector 1 and this is support vector 2. So I am having these two support vectors, which are the data points that is giving the clear separation between these two. So this way we can get a 2D linear dimensional linear SVM. This is again example of linear SVM where we are getting the maximized margin with support vectors, and this is non-linear, in which we have to add another dimensions in this area, so which is can be separated like this. So if we have to separate this data which can be separated by this, then we have to go with this dimension, that is we can have along with the x and y axis we will get the z. So here the equation will work as x square plus y equal to z square. So we have added the third dimension when we are working on the non-linear SVM. So this third dimension will give the separation in case of non-linear SVM. So now with this SVM we'll divide the datasets into the classes in this way, where we will get the best hyperplane, and it can be represented in the three-dimensional space. Hence it can look like a plane that is parallel to the x-axis if we convert it into two-dimensional space. And like this we have as seen we have in this image. So this is example of non-linear SVM in which we are having dimensions where x square plus y square is equal to z square, where z square is my third dimension in the case. So this is the case when we need non-linear SVM, which can also look like this. So this is my linear SVM and this one is non-linear SVM, in which we will get hyperplane in both the cases, and we will be having soft margins and the optimal margins in the case. So this is again if we are having this type of data and we want to organize it, then the kernel will get like this, in which we set the kernel or hyperplanes. We will get a model like this. This will be the diagram for non-linear separation in case classification in SVM. So we have various types of SVM kernels like linear, polynomial, radial basis, which are to be set on the dimensions in SVM cases.
SVM creates a line or hyperplane to separate data points into classes.
So in this case we are talking of having separate classes, like we are having flat class, which is a type of simple if it is, and this is also known as too simple.
A workaround to this limitation is to first apply
we can just try to understand this.
Data points before applying SVM. With this technique, we can easily achieve the desired effect of getting a nonlinear decision boundary without changing how SVM works internally.
So we are without changing, we are getting this point, that is getting the yes in this case. And in the next video we will do the implementation of this SVM kernel using Python. So thanks for watching the video.